Well, hello again. Today you'll be doing a spectrometric analysis for copper. In doing this, you'll use a lot of the techniques you learned earlier, so let's review those. Today's analysis will be made using a spectrophotometer. A schematic diagram of this instrument is shown here. A lamp similar to what you find in a slide or movie projector generates a wide range of wavelengths or colors of light. This goes to the grating here, where the colors are separated into a rainbow, and then the correct color of light needed for the analysis is selected by the slit here and allowed to pass through the sample, which is over here. The amount of light which ultimately passes through the sample then is measured by this phototube. This is recorded on the meter as percent T, that is the percent of light transmitted through a sample. So the lamp generates the light, the grating separates it into its components, the slit selects the right component or color of light, allows it to pass through the sample, and the phototube then measures the amount of light which actually passes through the sample. For our copper analysis, we'll make solutions which are blue in color. Things which are blue strongly absorb yellow light. That's the complementary color of blue. So for our analysis, we'll use light of wavelength 625 nanometers, which is yellowish. Now, the more light absorbed, the more copper is present. Or in other words, the smaller the percent T, the more copper is present. Now let's look at an overview of this analysis. To measure how the spectrometer reacts to the blue copper color, we'll first measure standards. Your standards are carefully made solutions of copper which allow you, or at least the computer, to know their exact concentrations. These are measured in the spectrometer to see how much 625 nanometer light each transmits. Now, the blank is distilled water, and it's important because it allows you to determine how much 625 nanometer light is transmitted through your cuvette in the absence of any copper. Now, once you know how quantitatively the spectrometer responds to these solutions, you will prepare solutions of your unknowns and measure them. Now, the percent T's obtained here and from your standards will allow you to measure the concentrations of your unknowns. Now, please note, in doing these measurements, use the same cuvette and the same spectrometer for all the measurements. Now briefly, let's look at the chemistry of this analysis. Two major chemical reactions involved in this analysis. The first involves the dissolving of copper metal with nitric acid and generates a lot of NO2. Now this must be done in the hood. The second reaction converts the blue copper ion into the intensely blue copper amine complex. This increases the sensitivity of the analysis. This intensely blue color of the copper amine can be measured at much lower copper concentrations. Now let's turn our attention to the experimental details of this analysis. First, a warning. Handle concentrated nitric acid carefully. If it gets on your skin, wash it off with plenty of water, but in any case, it'll probably stain your skin yellow, as you can see here. You'll start out by dissolving your copper standard in concentrated nitric acid. You saw that reaction earlier. Now, after your copper is completely dissolved, you'll want to add ammonia to intensify the color. You'll do that in two steps. First, you'll use 6 molar ammonia, then concentrated ammonia. Let's see how that's done. We'll start by rinsing off the watch glass so we don't lose any copper. Now we'll start adding the 6 molar ammonia here. We can add that. As you see, as you add it, you get this darkening color here, but that has to be a permanent color. Now we'll start swirling it here. There, now you see it's getting really blue there. Okay, now you see this change color. Now, in a little while this will precipitate here. At this point, well, we could add maybe just another drop or two here. Okay, that's it. At this point, we'll add the concentrated ammonia, and now we're ready for the quantitative transfer to the volumetric flask. In a quantitative transfer, you'll want to make sure that all the copper is transferred from the beaker into the volumetric flask, down to the last fraction of a microgram. To do this, you will use a funnel. And a wash bottle, and the wash bottle is filled with distilled water at room temperature. Then you'll take your solution and pour it in, but do this carefully so nothing splashes out. And don't tilt it back until you rinse off the lip so that you make sure that all the solution that's at the lip is nothing but distilled water. That way, if anything runs down the side of the lip, it'll be distilled water rather than copper. Then you rinse the flask again, and you do this again. Again, make sure that there's nothing on the lip but distilled water. Do a third rinsing, or second rinsing here. Again. Then rinse the inside of the funnel. Make sure all the copper is out of there. Bring it up, rinse the outside of the stem, and you're going to quantitatively transfer it. At this point, check to see whether or not the solution is at room temperature or not. If it's not at room temperature, you can cool it in some cold running water. But at this point, then you're ready to fill this up to the mark. Now, you'll fill it up with room temperature distilled water to just below the mark, and then add the distilled water dropwise until you get it just to this mark over here. Until just the bottom of the meniscus should be just at that mark. There you go. It's right at the mark. Now, cap it and we'll shake it. To mix it, hold the stopper firmly and shake vigorously about 12 times. When you're through, you'll be all set to start making solutions to measure in the spectrometer. All right, here we are at the spectrometer. Now, you're going to make several solutions today, 2 from your standards and 1 each from your unknowns, and you're going to measure them in this spectrometer. You will bring these solutions to the spectrometer, and when you do so, the solution should be in a cuvette. This is the cuvette here, and it has the blank in it, and you should carry this in a beaker so that you don't get fingerprints on it. And you should also bring in a paper towel so that you can wipe the cuvette off before you put it in the spectrometer. Now, the first thing you do when you get to the spectrometer is make sure that the wavelength is set at 625 nanometers. To do that, you can twist this knob if it is not set right. And even if you have set it once, make sure you check it each time you use it, because someone else may have accidentally readjusted this thing. Now there are two other controls on the spectrometer here. What you want to make sure is that when no light is passing through the sample compartment, the meter reads 0%. And when the light which is passing through distilled water, it reads 100%. So, to do that, this is the sample compartment, and it's empty at this time. Make sure you close it, because you see if you open it, you can get stray light coming in. So it's closed. And then adjust the needle so that it goes exactly to 0%. Now the 0% is adjusted. Now you'll take the reference cuvette. Now this is called the reference cuvette. It stays with the spectrometer. Do not move that reference cuvette around. It stays with the spectrometer. This reference cuvette then has nothing but distilled water in, and you wipe this off again with your towel, and you put it in the sample compartment. Having nothing but distilled water, it should read 100%. If it does not, you can adjust it so that it does read 100% with this other knob, this second knob on the front panel here. So now you have the machine adjusted so that with nothing in, it reads 0%. With the reference in, it reads 100%. At this point then, you can start making your measurements. Now to make these measurements, let's take a little closer view here and get this thing really set properly. Okay, here we are at a close-up here. As you see, we're a little bit off the 0%. So we'll adjust it so that it's exactly 0%. And now we'll put the reference cuvette in. Let's get the reference here. Again, line up the trademark and set that up so that it is exactly 100%. There it is. Whoops, the law. There we go. All right. So, now the machine is set exactly. Now we will put in our cuvette, the one that you're going to be using, not the reference. This is your regular cuvette. It's going to have nothing but distilled water. This is called the blank. We'll see what your cuvette reads with distilled water in. The machine's cuvette reads 100%. You use it to set the machine. Your cuvette may read something different. So let's put it in here and see what it reads. Now we don't do any more adjustment, we just read. And you see it's reading a little over 100%, so we'll have to estimate. I would say that's 102%, 102.0%. Now, you'll go through everything we did a second time to make sure everything is reading right. Then you will go back and make a solution and bring your solution to the spectrometer. Let's do that now. Okay, we have another solution here. This is B, say our standard or something of that sort. Now what we're going to do is just go through everything that we have done. We make sure that it's reading 0 with nothing in it. Now we're going to put the machine's reference in. Again, I'll clean it off so I don't have fingerprints in case somebody accidentally handled it improperly. Always line up the trademark with the mark on the sample holder there and adjust this exactly to 100. There we go. Now the machine is set, back to 0. And again, line up the trademark with the mark on the sample holder and put in our sample. And now we read our sample. Our sample is reading 56.6 or 56.7. Well, it's drifting up a little bit. There will be a little drifting. That's why you read it twice in a row. Now, 56, we'll call that 56.8. Now, we could reset this again, make sure it goes to 0, make sure it goes to 100%, tweak it up there just a bit, and put in our sample again. Wipe it off before you put it in, make sure you got all the fingerprints off, line up the trademark, put it in, and we're reading 56.9%. So we've duplicated that reading. Let's take a close-up at something called a parallax error. All right, here we have another sample in the spectrometer, and if we do the reading, we can see that it is reading 39.2 or 39.1% transmission. Now you see that you cannot see the reflection of the needle in the mirror here. You see there's a mirror, you can see the reflection of the pen, but you can't see the reflection of the needle. That means that you're looking directly on, and this is a correct reading. If you see the reflection of the needle in the mirror, you have to move your head. And if you still see it, you should close an eye. Now let's take a look if we move the camera so it in fact will give us a parallax error. Remember, we're reading right now about 39.2. Now we move the camera so we're well off to the right, and as you can see now, there is a reflection of the needle in the mirror that you can see. And now, instead of reading 39.2, because we are looking at it off at an angle, it is actually reading something like 40.2. This is the parallax error, and this is something that you should avoid. After you finish making measurements with the spectrometer, you can put your data directly into the computer. Well, I think you've got enough information now to do the experiment. Best of luck on it, and I hope you have fun.